So, what is the stimulus for hearing?
Sound.
And then what is sound?
Waves.
Waves of what?
Vibration.
Sound. By
So it's vibration of
The membrane in our inner ear.
so it's kind of when we think of sound, it's usually these compression waves going through the air, right? You know, I am supposed to be my mouth. There's my little uvula, and then down in my throat are my vocal cords. This is supposed to looking down my throat here. You know, the vocal cords are basically vibrating back and forth as I'm talking. Those set up these compression waves in the air. Every time my vocal cords push out and back, it creates this wave front of air molecules that are now kind of going out into space. You know, in this case, it's actually going into my microphone, which is then getting transformed into an electrical signal going through your computers and coming out your speaker. So on the other side, there is the speaker in your computer or your phone, and the speaker cone is actually vibrating back and forth and setting up little compression waves in the air. And then finally, here's your ear. This is supposed to be you and your eardrum. And the eardrum is basically vibrating back and forth in response to those compression waves of air that are coming in.
So what are the air molecules?
Oxygen and nitrogen, just atoms.
All of those.
Yeah, they're just little, they're atoms and molecules, like O2s and things like that. 21% of them are O2s and most of the rest are nitrogens.
So all the chemicals that are present in the air are the air molecules.
Yeah, air is just a gas. It's just, when we get to the respiratory system, it's again about 21% oxygen, about almost all the rest nitrogen and little bits of other things. So we have this movement. It's a physical movement of your eardrum, and that physical movement is going to get converted into electrical signals that go to your brain and you perceive as sound. So let me talk a little bit about that. So this is supposed to be the skull. I'm going to, so this is the skull. Here's the brain. Here is your ear. This is like my external ear. The actual like ear itself, we call the pinna. Then we kind of come in. There's like kind of that ear canal. And now within the skull, there are going to be two different things that are going to be important. The first one is going to be the middle ear, and the second is going to be the inner ear. And the middle ear has the eardrum here. Eardrum called the tympanic membrane. there's a little membrane that leads into the inner ear called the oval window. The inner ear, this is where we're going to find the cochlea, which we're going to talk about in much more detail later. The inner ear does sensory transduction. This is what converts the vibration into an electrical signal. This is going to end up creating the nerve that goes to the brain, our cranial nerve 8. So the cochlea is going to convert vibration into an electrical signal. So that is important to realize, that the inner ear is where we actually do the magic of creating movement into electrical signal to the brain. The middle ear is more of a place to transmit the vibration. And again, we'll talk more in lecture, kind of do impedance matching, make sure we're efficiently transferring the vibration, which is in the air. And we need to transfer it into the fluid-filled environment of the inner ear. So we have these little bones, they're called the ossicles. The little inner ear bones, the ossicles. They're like a little lever system that as the eardrum moves back and forth, these little bones transfer that vibration into the inner ear. And then it's important here in my picture to remember that all of this is located within the skull. So typically, if you are hearing and everything is working normal, you've got air vibration coming in. That air vibration then will wiggle the eardrum. Then through these little bones, that's going to wiggle this oval window. So all this so far is just mechanical conduction, transmitting the vibration mechanically into the inner ear. Once we get to the inner ear, then we have something different happen. Then we have the electrical conversion, and we send an electrical signal through the nerve into the brain. So there's two things going on here. One is getting the vibration into the inner ear. The second thing is then in the inner ear, convert the vibration into an electrical signal. So is that part clear? So I kind of drew this out. What is another way that you could get the inner ear to convert vibration into sound without having it coming in at the eardrum?
You cover your ears and you listen inside. I don't know.
The fact that it's just embedded in the skull, if you just vibrate your skull directly, that will still stimulate that inner ear. So like when we get into these tests that we're going to look at, sometimes you just take a tuning fork and you just put it right on the skull. And this tuning fork is vibrating, which then vibrates the entire skull, which is then going to wiggle the inner ear and you'll hear something. So you can feed the vibration directly into the inner ear through the skull. This is called bone conduction. Versus over here, I have air conduction. So So that is going to be important when we are looking at these tests to assess hearing loss, is understanding that there are two different ways that you can conduction. There's two different no, I spelled it right. There's two different ways that you can stimulate this. The normal way, which is air conduction, which in general is much more efficient. The ears are designed obviously to work to detect air vibrations. But if you put a tuning fork directly on your skull, that will also create sound by vibrating your inner ear, which then converts that vibration into a perception of a sound. So that leads us now into the two main kinds of deafness that you can get. Or actually types of hearing loss. So one is if the sound just never gets to the inner ear. That's called conduction deafness. So conduction deafness, what are some ways that you think you could have conduction deafness, that the signal never gets to the inner ear?
Ossification of the little bones inside the ear.
The ossification, sometimes those little bones get calcified and then they don't move properly. So even though the eardrum is vibrating, you don't actually have any vibration transmitted to the middle ear. I mean, to the inner ear. What's another thing that could go wrong?
Damage to the eardrum.
Yeah, a perforated eardrum, something wrong with the eardrum, that's gonna also cause the same problem. What else?
Something wrong with the organ of Corti in the cochlea?
So that's different, right? That's where we have the sensory transduction. Right now, we're gonna get there, but for right now, it's the things that keep the vibration from ever getting to the cochlea in the first place. So, you know, if you
Something wrong with, sorry, I'm sorry.
say it again.
I was about to say if there's something wrong with those two special muscles that actually helps in vibration of the,
Oh,
the
interesting.
ossicles.
I have never heard of that, but that's, you know, theoretically, I could imagine that. More obvious things would be just like, you know, a lot of earwax. You just have so much stuff clogging up your ear canal that the sound's having trouble getting in. Or else you can have an ear infection where you have all sorts of goo in your middle ear that's pushing out against your eardrum and keeping it from vibrating. Right? So there's anything that keeps the sound from getting into the ear canal, or keeps the eardrum from vibrating, or keeps the little bones from transmitting the vibration to the oval window. Any of that could be something that causes conduction deafness. So are there questions about what I mean by that?
You mentioned the ossification of ossicles.
Right.
Do you mean that those bones are not moving as it's supposed to?
Exactly, exactly. You get kind of an overgrowth of the bones, the joints don't move anymore. So even though the eardrum is vibrating, that little lever system isn't working, so you're not transmitting that vibration to the inner ear anymore. So, and that's not that uncommon. Some older people, it's a pretty common surgery to go in and try to free those up, or sometimes even bypass them altogether. The other kind of hearing loss that you can get is if all that stuff is working, but the inner ear doesn't do its job. And that's called sensory neural deafness. So I'm going to say versus so sensory neural deafness is when the inner ear is not converting the sound into a electrical signal. And again, we're going to look at this in much more detail later. The idea of the little hair cells that are basically converting motion into voltages. But something is going wrong in the cochlea. The cochlea normally converts vibration into an electrical signal. If that's not working, you'll also not hear anything. Sensory neural deafness can be further down. It could be also in the nerve or even in the cortex or something, but something on the neural side is not working. It's not the sound is getting where it's supposed to. It's just the next steps of converting it into an electrical signal and a perception are not working. So, are there any questions about, this is kind of all the background information you need for this next part to make sense. Everybody's got it? Okay. So, there are going to be 3 parts to this, this hearing lab. Each one is pretty short. The first one you're going to have to do at home because it requires people to kind of work with each other, kind of in the same space. The second part we're going to actually be able to do all together using a little video. I think, the vision, actually, did anybody, I could just ask briefly, I did post a link to a YouTube thing for that motion after effect on the module. Did anybody notice that and try that at home? No? Highly
The
recommend
one that
it.
you showed in the class?
Yeah, that I showed you in class, but it kind of stunk because
I didn't see it in the model. Let me check.
I think it's in the lecture module. Hopefully I activated the link.
Yes, it's in the very first thing in the module, vision module.
No, I don't think it's in the vision module.
No, it's in the remote
Yeah,
lecture week 8.
Yeah. Remote lecture week 8. So do this, don't do this now. Do this later. But that YouTube visual motion after effect, if you've never done it, it's so weird and cool. You know, and again, it didn't really work well through the computer Zoom thing, but it'll work well on YouTube on your own personal computer. The thing we are going to do together is an auditory thing, and that also might not work well. In fact, you'll have to turn on. Does everybody know how to turn on original sound on your Zoom thing? Do you know about that? If you've ever tried to do any kind of musical things through Zoom, you'll notice pretty quickly that it just gets all garbled weird because it does all this processing trying to make, you know, voices sound good and noise go away, but it's really messing with the signal. So up at the top of your screen is usually a little thing. It's like next to the little shield thing, like turn on original sound. Do people see that? Like on my thing, it's just like a little thing. It's easy to find. if you guys can't do that, then this is another thing you're going to have to do at home, because if you're trying to do this sound thing through a normal Zoom, it's not gonna, you won't hear it. Okay, so I was thinking it was going to be fun to do together, but I'll just tell you about what to do there as well. All right. All right, yeah, no, I have to say, I'm going to be happy when we're all in the same room again. All right, let's talk about the three parts to the hearing lab. So the first part, we've been talking about depth perception using two eyes. Now what we're going to do is we're going to talk about sound localization. Where is that sound coming from? Right? Even if you have your eyes closed and your cat goes meow, you probably know, is it over there or is he over there? How is it that you actually can figure out where is that sound coming from? And a lot of it has to do with the fact that you have two ears. So these are supposed to be your ears. The other reason this is going to work is because sound is really slow. Light is instantaneous. Light is, what is it, 186,000 miles per second. If you look at sound waves are only traveling, what is it, 300 meters a second? It's pretty slow. Like if you've ever watched lightning and then like 5 seconds later, okay, there's the sound. The sound took its sweet time to get to me. Even if you've ever, I remember just camping at a lake and looking across on the other side of the lake, and there's somebody chopping wood and they're going, it's like, even, sound is pretty slow. And your nervous system, even though I've been kind of given it some grief about how slow the neurons are and everything, it's fast enough to detect differences in sound arriving at one ear at another ear, because sound is also really pokey. So if I have, here's, let's say somebody is hanging out and all of a sudden a fly is on their head and going buzz, 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 buzz. You'll hear this buzzing fly. That sound is going to be perceived differently between the two ears. What are the two different, there's two different qualities of that sound that are going to be different. What are the two different ways that the sound is going to be different at one ear versus the other ear in this case?
It's going to be lower pitched on one side, and it's going to get there slower.
So the pitch won't be different. Like there's
The
no
volume
reason
would be
for the
different.
pitch to be different, but it's gonna take longer. It's not going to go slower either. It's right. It's going to be the same speed. It's always going the same speed. But because it's going the same speed and this ear is closer, it's going to reach this ear first, and I'll get to this ear second. So we're going to have what's called an interoral, it just means between ears, time difference. Right? It's because it travels at the same speed no matter what here, and that buzz is going to hit here before it hits here, because it's a longer distance to get to here. What else will be different given that this ear is further away?
The volume.
The volume, exactly. So there's also going to be an intraoral intensity difference or volume. So these are two important clues that your body, your brain uses to know that this little fly is buzzing off on the right rather than buzzing off on the left. If, you know, if there's some other little dude buzzing over here, it's going to be the opposite. It's going to arrive sooner and be louder in this ear. So using this information, my brain will give me a sense of where in space is this sound originating from. What is going to be the hardest? What position is going to make these clues not so useful?
When they're in the front, in front of you, the same distance.
Exactly. So if I'm looking exactly on the midline, they're going to reach both ears at the same time. And if it is in front of me or in back of me on the midline, it's still reaching both ears at the same time at the same volume. So do you think it's going to be easier to tell right and left or front and back in terms of localization?
Right and left.
Yeah, right and left. Right and left, you've got these really nice clues, or sometimes we call them cues, that give you information. Is it more on the right or more on the left? But if something's more towards the front or the back, you don't have as much information. It's a lot trickier. There is still some stuff just based on the shape of your asymmetry of your earlobes and things like that. But it's trickier. So in your lab, it asks you to use a little bell, but you can just use your fingers. You can just snap. And the basic idea is, again, you're going to have, if you don't have somebody to work with, just kind of describe what you see in the video, but hopefully there's somebody around you that you can do this with. You're basically going to have them just kind of sit there. And then you are going to kind of silently, you don't want to, be a ninja. You don't want to be clomping around so they can figure out where you're walking. You kind of just go and then like snap, make a sound. Snap in front of them, snap behind them, snap to the left, snap to the right, snap on top of their head, and record how well did they localize it. Were they spot on? It's like, oh, they're pointing right where I snapped, or I snapped here and they're pointing like in the wrong direction. So that's going to be the first part of this lab. Part one is you're going to have your subject sitting here with their eyes closed. Give them a blindfold. Or just have them, if you trust them, just have their eyes closed. And you're going to snap, behind and front, above, to the left, to the right, and record your data and say what it means. And again, when you're discussing it, put it in the context of what we've been talking here. What did you observe, and does it make sense given what we know about how you figure out where the sound is localized? So, any comments or questions about that one? Okay, so that's hearing part one. Sound localization. You got to do at home. It's not going to take too much time, right? You just have to find a willing participant and snap around them and just record what you find. So hearing part two. This part is going to be about frequency of hearing. So we've been talking about frequency now in the context of that nerve stimulation lab. What is frequency? What does that word mean?
Number of cycles per second.
Exactly. So if the sound waves are vibrating at a certain frequency, that's just how many compression pulses you are getting per second. And again, it's in hertz. If I have something that is 440 hertz, this is like, A on middle A on the piano. So different, and this is where I if I'm in the lab, I have all my tuning forks, and then I can probably just like can you hear that?
Yes.
So that, in fact, well, let me get the A. So this is probably about 440 hertz. That what you're hearing is that pitch is actually your eardrum vibrating back and forth 440 times per second. If I double it to 880, what your experience in terms of pitch is going to be going up an octave. It's like if this is like do, do, re, mi, fa, sol, la, ti, do. That is double. This would be 440, this would be 880. If we double 880, what is it going to be? It's going to be 1720. It's going to go up another. Every time you double the pitch or double the frequency, it goes up an octave. So when we think of pitch, and it's not exactly, there's ways to fool it, just like you can have visual illusions, you can have auditory illusions. But in general, when we hear a certain pitch, it's giving us a readout of what is the primary frequency of the sound that we're hearing. In fact, where's my little tone generator? I mean, can you all hear that? So this is like, 1,000 going up to 3,500. Now I'm at 5.5 kilohertz and going up. So your experience of pitch is just how high or low the frequency is. As just like your vision gets worse as you get presbyopia as you get older, your ability to discern higher frequencies gets worse as you get older. They call it presbycusis. So, like if you are really little, you can probably hear sounds upwards of like, up to like when you are kind of young, like most of you all probably, make you look kind of groovy. I don't know. You can still probably hear up to like 17 kilohertz or more. As you get older and older, I don't know what I look like actually, but like me, when I do this, I'm down around like 13.5 kilohertz. And above that, it's silent. I've done this with my mom, who's got actually pretty bad hearing up in her 80s. She's down around maybe around 3 kilohertz, where so as you age, the highest pitch that you can determine, that you can actually hear, gets lower and lower and lower. And it's pretty dramatic. I mean, this is, again, in the classroom, it's always really fun to do this because I'll play these pitches And as soon as you start getting down around 16, 17, 15 kilohertz, you have this thing where half the people are saying, turn it off, it hurts my ears. And half the people say, it's dead silent, I don't hear anything. Again, you just kind of, you're not going to get that experience, this way, because now it's more theoretical to you. But it really is dramatic. I mean, there are supposedly there are ringtones that high school kids use that are up here, that they can hear each other like texting each other, and the teachers don't hear them because the teachers are down here. And the opposite, you have like people with liquor stores who will play these sounds up here that are super unpleasant to high school kids, but their desired clientele don't hear them at all. So it really is pretty dramatic what you can hear or not hear. And I should mention, this is humans. If you have like a cat, you've probably, I definitely know a lot of you have cats because I've seen people with cats here. You've probably noticed your cat's there. It's like, whoa, like the cat's totally, there's something there, and you have no idea what the heck's going on. They hear up around like 50 kilohertz. They can hear stuff that's like 3 times the frequency pretty much, that you can. And so they're like mice. Mice speak in these ultrasonic, like when one mouse is talking to another mouse, you don't hear it. It's dead silent. But a cat hears it as like, whoa, the mice are here. So, and that's that whole point, or the idea of a dog whistle, right? A dog whistle. You blow this dog whistle and you don't really hear it because it's in a frequency above what humans are used to hearing, but the dog hears it. Or now in politics, they use it as someone saying something that one person can notice and another person doesn't notice, if depending on what kind of clues you're tuned into. But the idea here is, as you get older, the maximum frequency you can hear goes down. There is a cool little thing that actually works pretty well. Although, again, I don't think it's going to work over Zoom because of the sound filtering that Zoom does. But what I want everybody to do under this doing the hearing lab, frequency range of hearing, it says part A, ignore this part. So ignore that part. Don't do part A. B, using the videos below, determine the maximum frequency you can perceive and record that value. So, here we got this dude, how old?
This is Joe and Tel, and today we're going to try to find out how old your hearing is. But one thing
we can keep,
as we age, to try to, this is how the
blah, 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 blah.
Then keep it at,
so
not work if you're using your phone or a laptop. So also,
so it's better to do it with headphones because he does right and left ear, but I don't care. If you just do it in the air, that'll be fine as well. But basically, down, I should say, here he's doing like the age where you would probably hear this, but down here, what I really want you to pay attention to is the frequency in hertz that's down on the right corner here. So listen, and at some point, you'll hear a sound like, hey! When you start hearing it, notice what the frequency was and write it down. Yeah. Like for me, it was just like, I mean, I don't know what you're hearing. Like for me, until it was getting into the 1300s, it was dead silent. Whereas when you do this, I'm sure you'll hear something at a lower one. So, just you keep going. Right now, it's just really unpleasant. But so I want each person to do this at home and to the best of your ability, figure out what is your highest frequency. And I did include some data from previous classes. Just so you can kind of see what it tends to look like. You typically get something like this. But what it would be fun if you all can just email me your data. I can put it into a spreadsheet and we can actually see what the class looks like and actually create one for ourselves. So, but anyway, the basic idea here is you are going to find the highest frequency you can hear. And then again, in your discussion, put it into the context of what happens when you look across many people across different ages.
I have a question. How do we kind of adjust for like the volume? Like, what if the video kind of plays at like a lower volume than like what our headphones might be? And I don't
It
know.
doesn't matter. As long as it's loud enough to hear, you'll either hear it or you won't.
But wouldn't that give like a false?
No, because even if it's loud, if it's a frequency outside of your hearing, it would be like, what if the radio waves are really strong? It's like, I don't know. It doesn't matter, right? It's like, I just don't have the ability to detect there's anything there.
Okay.
Um, you know, that being said, there could be kind of noise or something that's coming through, but in terms of the actual signal, the frequency, you should either hear it or not hear it. Depending on the volume, it will be kind of maybe quieter or more piercing, but it'll still be present or not present.
In terms of putting in the larger context of the why, I feel like I kind of an idea of why when you get older it gets lower, but how would you explain it?
That has to do, and we're going to go more into that. That has to do with kind of hair cells dying in your cochlea.
So for now, just saying that this is the general trend across age groups as we can see from the data, but not going into an explanation of.
Yeah.
Okay.
Yeah. Right. So, but yeah, back to your thing, Lauren. Like, if you played a sound at 16 kilohertz and just cranked it up higher and higher and higher, there would be like half the people in the class just like screaming in pain, and I would just be like sitting around, doo, doo, doo. I don't care, right?
Mm-hmm.
Because it doesn't matter the volume. What matters is if it's like sticking a needle into my nervous system.
Okay.
All right. So that's part two. And again, it's taken me forever to explain all this, but doing it at home on your own it's going to take you like 3 minutes, right? All you got to do is find where is the value where you start hearing the sound and kind of record that. And then again, in your write-up, integrate the idea of that top frequency across age and all that. The last part, where are we? We're doing all right. hearing loss. So the next part are going to be these two tests that look at hearing loss. I think what I'm going to do, I'm going to describe them briefly. Then I'll kind of show you a video, and then I'll just tell you what you have to do after you're on your own. So, there are these two really classic tests that people use in a clinical setting to look for hearing loss. They're both very straightforward. All you need is a patient and a tuning fork that you can vibrate. A tuning fork is basically a piece of metal, about 4 inches long, and you whack it and it goes bing, and then you can stick it on their head or hold it by their ear or whatever. The nice thing about the tuning fork is you can use it to either stimulate air conduction by just holding it near their ear, or you can use it to stimulate bone conduction by sticking the metal thing against their skull. Right? So we can use the tuning fork to either stimulate air conduction or bone conduction. And these tests are going to help us look at the two kinds of deafnesses as well. So this I'm going to say, can use for bone or air conduction. This is kind of my stimulus. And then what are the two kinds of hearing loss that we've been talking about?
Conduction deafness and sensorineural deafness.
Mm-hmm. So these tests are going to help us look to see if you have this or maybe some combination of the two. So this is kind of the setup. The basic tool, we can stimulate the auditory system either through the air like normal or through the bone by jamming it on your skull. And we're going to have these techniques to help us look for conduction deafness and sensory neural deafness. So let's do it. There's two of them. And they're both pretty simple. For each of them, you should understand kind of how you do it and how to interpret the results. So I'm going to kind of go over it right now. The first one is the Rene test. This one is you do one side at a time. And you start with bone conduction. So the idea here is your ears are optimized for air conduction. Air conduction should be better than bone conduction. But in fact, do you remember, if you've been in anatomy, what's that little bump on your temporal bone right behind your ear there?
Mastoid process.
Exactly. So I'm going to take my tuning fork. I'm going to stick it there on the mastoid process. And it's going to be vibrating in there. And assuming I do not have sensory neural deafness, it's going to be vibrating my bone, and I'm going to hear it, right? The idea here is I'm vibrating the bone. I've got bone conduction, and I'll hear some like bing in there. Right? If I didn't hear anything at all, even if I'm jamming this on my mastoid bone, what would that mean?
You have sensory neural damage.
Exactly, problem in the inner ear.
Yeah, there's some problem in my inner ear or beyond. Like there's some kind of sensory neural deafness. Because this should be stimulating my cochlea directly by vibrating the bone. So if I did not hear anything here, then I know there's something really profoundly wrong, that I have sensory neural deafness. So if
Is it vibrating at what if it's not vibrating at like a high enough frequency to recognize?
well, no, it's you always do this. This is like 512.
Oh, okay.
Yeah, no, these are designed to vibrate at a frequency that's just like kind of right in the middle of your comfortable hearing.
Okay.
Yeah. No, so they are designed so they have this kind of physical resonance where if you just start them vibrating, they will vibrate at that frequency every time. So, so in the Rene test, you leave that on, and after a little while, they won't hear it. As this thing kind of becomes less and less vibrating, they won't hear it anymore. But this thing is still vibrating. So at the point where they don't hear it anymore, you now take it and you put it side by side, but besides their ear here. So now it's coming into the ear versus air conduction. And air conduction normally is much more sensitive than bone conduction. So assuming that they do not have conduction deafness, when you move the tuning fork, again, you haven't stopped it. You kind of started it, it was there, and now they can't hear it. As soon as they don't hear it, you move it to now transmit via air into their ear canal, and they should hear it again, because even though it's vibrating kind of at a low level, the air conduction is usually much more sensitive. Typically, you should be able to hear it for at least as long as you heard it on when it was pushed against your skull. What would it mean if they could hear it when it was on their skull, but now when I moved it to their ear here, they can't hear it anymore?
A problem in the middle ear.
Yeah, middle ear, or more generically, more generally?
With the bones?
Or using those terms that we were using?
Conduction deafness?
Yeah, conduction deafness. Because it's middle ear, or it could be it could be in the outer ear, the ear canal, even like, wax buildup or something. That's why. So if they hear it when it's on their mastoid, but not when you then move it, to do the air conduction, that would say that there is some conduction deafness on that side. So that is the Rene test. So does that make sense? One of the little like mnemonics people use to remember which is which is like the Rene is the one that goes near your pinna, right? The pinna is like the name for your flappy doodle on your external ear. So the Rene test is the one where you actually take the tuning fork and start on the mastoid and then go near the external ear there. So, any questions about the Rene test? The next one is the Weber test. So the Weber test is pretty different. On this one, you take the tuning fork and you put it on the midline of their skull. So this is just going into their bone, and it's right in the middle. I should say midline. You know, sometimes they have it right on the middle of your top of your head or on your forehead. It doesn't matter. It just has to be on the midline of your skull. And this one, interpreting this one gets a little complicated. If everything is normal, what do you think you will hear? What will it sound like? Assuming there's no hearing loss of any sort.
That hum that you were describing, that hum.
And how will it be in one ear versus the other ear?
Equal?
Equal. So if there is no hearing loss, you'll just hear the sound equally in both ears. Or, I mean, the other thing is if there is hearing loss that's identical on both sides as well. So you can't actually distinguish between identical hearing loss on both sides versus no hearing loss at all. But the basic idea is what you're hoping is that it does not lateralize. It does not become louder on one side versus the other. But let's say it does lateralize. If the sound lateralizes, so let's say it sounds louder on this ear. So for instance, example. So let's say you put this on the midline and your patient says it sounds louder in my right ear than my left ear. What's one possibility there?
Deafness in the left ear?
It could be in what kind of deafness in my left ear?
Maybe sensory?
Yeah, sensory neural.
Conductive.
So it can be sensory neural deafness in the contralateral ear. So if it lateralizes to the right, it could mean that I have sensory neural deafness on the left. That's why it sounds louder here, because this ear just doesn't hear as well. But the thing that's counterintuitive or it can be conduction deafness on the same side. So if hum, if you like hum, and then you stick your finger in your ear, that's kind of mimicking conduction deafness, like hum. It actually gets louder in the ear that you're clogging up. Do you notice that? I'd like to see people do it. The ones that, so like hum and put your finger on your ear. So do you notice that? Because it's not intuitive, like
Yeah.
this, but once you do that, it's like, okay, it actually does happen. So when you're interpreting the Weber test, there can be two possibilities. One is if it's louder in my right ear, it might be I have conduction deafness in my right ear, or it might be I have sensory neural deafness in my other ear. When you take the Weber test and the Rene test together, you can often kind of figure it right. If I'm not sure which it is, but then I do the Rene test and it says like, no, this person has no conduction deafness, then I know, okay, no, that's not an option. It must be the sensory neural deafness in my left ear here. So that's why you do both of the tests. Between the two of them, you can usually figure out like what's likely going on with this person's hearing.
Could you explain why that is, why when you plug your ear with conduction depth, why it sounds louder?
No. Yeah, there's different thoughts about it. I am not sure. I think maybe it's kind of clogged up so the sound vibrates more in there but yeah,
Okay.
yeah, I can guess. But I don't have a definitive answer for you.
Okay. So you just say that there could be conduction deafness on the same side.
Right. I can say empirically it's true. For what it, who knows why it is, but I can say conduction deafness leads to it being louder on the side that has conduction deafness. So then, I know what I was going to do.
It looks like that when the sound is coming from outside, the sound does collide against our bones or skin, and then it creates a vibration through it. Uh, um,
Wait, say it again.
like the sound can be heard not only through the ear canal, but the sound can be collided against the skin or bone, and the vibration creates the
Right.
internal sound.
Right. So that's what that bone conduction is, right? Bone conduction is when the bone, but typically that's not nearly as efficient as air conduction. So most of what you're hearing is your eardrum vibrating the bones, vibrating your cochlea, basically. So, but you can vibrate the skull and hear that directly through that bone conduction. Right? That's the whole point of bone conduction.
Professor, one question. For example, at night, where do I live, there is no sound, and I can hear my heart, my boom, boom. That would be bone conduction?
That's
No?
it's also blood vessels within your ear making noises and squishing. Normally, you're pretty good at there's all sorts of sounds, internal sounds going on that you're blocking out. All sorts of visual stuff on your retina, blood vessels that you're blocking out. There's lots of information that your nervous system puts on kind of these filters so you don't notice all these processes going on keeping you alive. But yeah, I don't know. And I'll mention the other thing, like I definitely get, if it gets quieter, I get a lot of tinnitus, a lot of the ringing. The ringing that comes not from the ear at all. That comes from actually the cortex, where you have like these kind of weird reverberating circuits that are no longer working properly, and just hear stuff all the time, even though the ear is not giving it any input. So I'm going to go, I'm going to show you this guy's picture because he's just so weird looking. So the Rene test, Heinrich Adolf Rene, and talk about intense. That's the guy who first developed the Rene test. But
Mothers Against Drunk Driving supports Prop 22. 22 saves lives by preserving access to rideshare services across California, helping keep drunk and drug drivers off our roads. Please join Mothers Against Drunk Driving in voting yes on Prop 22.
The tuning fork tests are useful in assessing hearing loss.
so here, this is, you can see it's stamped with that 512. That means that this one, when you whack it on something, it will vibrate at 512 hertz, which is a typical tuning fork to use for these tests.
This video shows how to perform Rene and Weber's tests. These tests are performed using a 512 hertz tuning fork. The tuning fork can be activated by flicking it between your fingers or by tapping the tuning fork on the knee. It is important to explain the test clearly to the patient. So you're going to hear a buzzing. I want you to tell me which position it is louder in. So position A, this tests air conduction, or position B. Bone conduction is tested by placing the base of the tuning fork on any bony area surrounding the ear.
Position A.
When testing air conduction, the tines of the tuning fork should not be held parallel to the external auditory meatus. Instead, they should be held perpendicular to the external auditory meatus and about 1 centimeter from it.
So she is doing a slightly different version. The version, like in the other videos I'll show you, is the more classic, where you start on the bone, wait until they can't hear it, and then move the tuning fork to the external auditory meatus and see if they can now hear it with, so yeah, I'm never going to be able to talk as cool as her, but that's the basic idea. It's comparing the bone conduction versus the air conduction for one of the ears.
Again, it is important to explain the test clearly to the patient. So can you tell me whether you hear the sound loudest in your left ear, your right ear, or whether you can hear it in the middle? Place the base of the tuning fork in the midline.
The middle.
So this other one, which I'm not going to make you sit through with me together, but I recommend watching, goes much more in depth.
Weber and Rene test. The clinical examination of hearing
So she goes,
causes sounds on the affected.
This goes much more in depth with nice little visuals showing the idea of bone conduction versus air conduction versus the inner ear versus the middle ear. So this video, it lasts longer. It's like 8.5 minutes, but it's well done. And she doesn't have as cool of an accent, but it's still nice. So I recommend watching this one as well if you want to kind of get background on these two tests. Again, here's the Weber test. Vibrating on the top of the skull, going through the bone. And assuming that the sensory neural is working, you'll hear it in there. And again, if one of the sensory neural is not, it'll be louder in the other ear. Conduction deafness, and again, I can't tell you exactly why, but it's going to be louder in the ear that has conduction deafness. So then, after you've done that, there are 3 patients. You're not going to be able to do it on a person probably because you don't have tuning forks at home. So this is going to be kind of the longest part of the lab for you. It's not going to be that long. These videos take a few minutes each, but you have to, for each of these 3 patients, here I said, evaluate the results for patients 1, 2, and 3. Record the results in your lab notebook, like what was the result of that test. There's 2 for each patient. There's a Weber test and a Rene test. And then you have to interpret, what does it mean? What do you think it means for each test? Was the test normal? Did it mean there might be a problem? Together, what does it tell you? Again, the way these look, each of these, just to give you an example.
The Rene or Rene test is used to help determine whether the patient has a conductive or sensory neural hearing loss. The vibrating tuning fork is placed on the mastoid bone behind the ear. The patient is asked to tell you when the sound disappears. At that point, move the tuning fork from the mastoid bone and hold the tines close to the ear canal. If air conduction exceeds bone conduction, the patient will still be able to hear the vibrations in this position. Mary, I'm going to place this behind your ear. Tell me that you can hear the sounds and then tell me now when they stop. Then I'll move it in front of your ear and say yes when you can hear them and now when they stop again. Okay? Yes.
So she hears it. You can't hear it, but she hears it.
No.
Now she stopped hearing it.
Yes.
Now she hears it again.
Yeah. Okay, good.
So just, together, what do you think? What did that tell you about our patient there?
It was normal.
That's normal, right? She could hear the air conduction for just as long as the bone conduction. So that's what you expect. You expect once the bone conduction disappears, you still got some time left on the air conduction. What would it have looked like if she had conductive hearing loss?
She wouldn't hear the one that was on the pinna or shorter than the one.
What about if she had sensory neural deafness? How it would have happened here?
She wouldn't hear it when it was on her mastoid process.
Exactly. She wouldn't have even heard it when it was there on her mastoid process. So you're getting an idea of how that works, how you interpret that. The Weber test is kind of similar.
The Weber test is used to evaluate for conductive versus sensory neural hearing loss. A vibrating tuning fork is placed firmly on the vertex of the patient's head in the midline. She is then asked to tell you whether the sound is heard equally in both ears or better in one than the other. Normally the sound is heard equally on both sides. Be careful to hold the tuning fork by its base and do not touch the tines.
Which, I have had students grab, because the tines are the things that vibrate. So they would none of these tests are working, and it's because they're holding the part that are supposed to be vibrating and making the sound. So.
Can you hear that equally in both ears or better on one side? I hear it in both. Okay, thank you.
Again, so what does that tell you about her hearing?
Normal again.
Or at least can be heard on both sides.
Yeah, so it's either there's no hearing loss, or it could also be equal hearing loss, right? Because this can't distinguish if both sides have the same amount of hearing loss. So
if you moved it to either side, and then the hearing was the same, like if you moved all the way to the right and the hearing was the same, would that tell you if something was a little bit more about the deficit?
So that's where you bring in, you do this along with the
Rene test. Okay.
Right, so if you do the Rene test and there's no conductive hearing loss on either side, then you know that that's out of the picture. You still can't completely um, eliminate like a symmetrical sensory neural loss. For that, you would have to do something more advanced. So then there's two more patients here. There's this woman who's works with, there's this guy here, and she'll do Rene and a Weber test on him. Whack. You know, so you're gonna follow that.
I hear the noise on.
You know, and then she does another patient here, you know, and in a Rene test and a Weber test on them, on that person. And for those two patients, I also want you to record their results and record or interpret what those results mean. So does that make sense? And again, each of these is like a minute long. This isn't a big investment in kind of time, but you need to kind of understand what are the tests, what do they tell you, how do you interpret them. Like by the time you've done this 3 times, hopefully you're really starting to get a sense of, oh, that's what that test is like, that's what it's doing. So are there any questions about that stuff for the hearing lab?
One more time over the conduction deafness on the side that is louder for the Weber test. That you said that it's not so intuitive.
Wait, so say that one more time, Jamba.
Could you go over the conduction deafness on the side that is louder for the Weber test? You said that that's not so intuitive.
It's not, at least for me, it's not intuitive that the ear that has the deafness actually sounds louder, which is, you know, normally you'd think the ear that has problems is not going to hear as well. But when you're doing this isn't a tuning fork, but pretend it's a tuning fork. When you're doing this thing where you are vibrating in the midline of your skull, the ear that has conduction deafness is going to actually sound louder. And again, the way I think about it, like if stick a finger in your ear and I'm talking right now, like this ear that's clogged up is way louder than my ear that's not clogged up. So that's why I'm saying it's non-intuitive. You know, the ear that has deafness sounds louder. You know, to me that sounds weird. That's why I always kind of double check. No, I guess it's true, even though it sounds weird.
Yeah, it makes sense. Okay, thank you.
And then yeah, I'm trying to figure out just in terms of for the taste, for the olfaction, and I was trying to be a little more ambitious, but I think what we're going to do, the one thing I would like you to do for the chemoreception, there's one of the parts of the lab that I think is really interesting and is useful to see. So I'm going to chemoreception. You have senses that detect the presence of different kinds of molecules. Smell, taste. In both cases, what is the stimulus for chemoreception?
Molecules.
Yeah, different kinds of molecules. If we are in smell, basically it's molecules floating in the air. Go up to your little olfactory epithelium, and different shaped molecules are perceived as different smells. In fact, let me just share that with you. I put it actually in the module, some pictures for you to look at. If we, and again, I'm going to edit. In fact, I'm going to edit this right now, and I'm going to just delete this. Part 2, you're not going to do. Actually, I'll say skip this. So we're going to do, so if you take a look, this thing here, molecule, if this molecule comes into your nose, you have the experience of smelling raspberry. If this molecule comes into your nose, you have the experience of tasting apple. If this molecule comes into your nose, ew, it's urine. You know, this one is chocolate, this one's skunk, this one's peppermint, this one's eucalyptus, this one's jasmine, this one's lemon, this one's marigold. So the sense of I smell pine or I smell dog poo or whatever, that's just a particular shaped molecule coming into your nose, and that is the way you perceive it. Just the way you perceive 440 hertz air vibration as some musical note, or a frequency of electromagnetic radiation as, oh, that's red light. You know, you detect this molecule as the smell of lemon, or this molecule as the smell of jasmine. So that's all smell is. Smell is detecting molecules. This is showing, you know, the smell of common flowers. These are actually the molecules that are actually detected that create the smell in your consciousness of that, the smell of a rose or of a violet or of a hyacinth or something. So just kind of putting that out there. Your sense of smell is this really kind of nuanced like chemical detector. But instead of reading out saying you are detecting like 2, 3, 4, blah 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 blah, blah, like you know gamma aminobutyric acid blah 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 or N-methyl D-aspartate molecule, it's like, oh, that particular molecule in my consciousness is the smell of jasmine. But it's the same. It's stimulated by a particular molecule. Taste buds are a little simpler. Taste buds are also chemoreceptors, but instead of detecting such a wide array of molecules, what do taste buds detect? What are the different kinds of molecules your taste buds can detect?
Salty, sweet, umami.
So electrolytes, you know, which is salty. When we detect things are salty or not salty, there's sodium chloride there or not. What about sweet? What is sweet detecting?
Glucose.
Glucose.
Or simple carbohydrates. In fact, glucose does not activate these as strongly as like fructose. So like fructose tastes, the same amount of fructose tastes sweeter than the same amount of glucose. Salt, sour. What does it mean if something is sour?
Citric acid.
Acidity.
Acid, low pH. You know, sour just, so this is giving you information about the food you're chewing up and dissolving in your saliva. So if it's salty, I know there's like these electrolytes in there. If it's sweet, I've got simple carbs. Sour, low pH. Bitter,
high pH.
or in general, these things called alkaloids, kind of a class of molecules often found in plants, often that plants make to protect themselves. A lot of times they're poisonous. So if you're going around eating plants, you typically want to know if there's alkaloids in there because they often can affect you. Not all alkaloids are bad. Caffeine is an alkaloid. Caffeine is very bitter on its own, but it also kind of wakes you up and makes you feel good. But in general, your sense of taste, you're chewing things up, dissolving it in your saliva, and then you have these little chemical detectors, molecule detectors on your tongue that are telling you, oh, it's sweet. There's simple carbs, good energy source. I like this. I want more of it. Salt also. You need salt. If you don't have ions, you're not going to be able to run all the electrical activity in your body. It's like salt. Also like that. I want that. I need to get that in my diet, bring it into my body. Alkaloids, bitter. I better like pay attention here. There's something here that might or might not be okay for me. So, taste buds are just a way of chemically analyzing your food on these kind of first approximations to see, is it something that I need to bring in, some salts, some carbs for energy, things I need to watch out for. So does that make sense? The thing that is important to remember, though, is even though we're saying this is taste, it's really very narrow. It's just actually telling you, is there the presence or absence of saltiness? The presence or absence of sweetness, of sourness, of bitterness. A hamburger isn't just purely salt, sweet, or sour, or bitter. Chocolate ice cream isn't purely salt, sweet, sour, or bitter. A potato isn't, it's like, when we think of the idea of that tastes good, or that tastes all right, or that tastes pretty crappy, it's not just your taste buds. Your taste buds are just doing this limited analysis. And in fact, when you have a cold, you can't breathe and everything just doesn't taste like anything. It all food tastes like cardboard. Your taste buds are working fine. You can still detect salt and sweet, but you're missing out on the lion's share of what we actually usually think of as like taste. So when we talk about, taste, in a normal sense, kind of in a popular sense, like, tastes yummy. What are we really saying? It does include your taste buds.
That the olfaction and the gustation both are working together.
So a lot of olfaction. A big part of what the flavor of your food is actually the more nuanced chemical analysis that's happening in your nose. That has a much wider array of molecules that it can convert into this sense, this experience. So the taste buds, this gustation, is giving you information on sweet, salt, sour, bitter, but the olfaction is giving you much more information on kind of the subtle, like, yummy or not yumminess of thing, or what is this? What exactly is this food? Is this a lemon, or is this a orange, or is this an apple, or is this avocado, or whatever? And actually, avocado. What's the other thing? If you have an avocado in your mouth versus an apple versus, what else? What's the big difference between those in your mouth?
The texture.
So the texture is another big part of it. So when you're trying to identify, is that a carrot or is that an avocado? The texture is going to be a big part of it. Not just what does it taste like, not just what does it smell like, but even what does it feel like in your mouth. So when we're doing like kind of food identification, which is going to involve all the different things that you normally use, you connect with that experience of what does it taste like? You know, these are all important. And so there's a cool experiment. Normally we actually provide you with food in lab, but you're going to have to do this at home. So what I am going to ask you to do at home, and this is fun, and this will be in the last few moments. Yeah, we've got 5 minutes, so this is just the right amount of time to explain. This is the only thing I'm going to ask you to do for the taste and olfaction. So this is part 2 of the gustation and olfaction lab. And this is only do part 2. Forget about the rest of it. Just do part 2. And the basic idea is you are going to make, 5 is about right. You should have, around 5 food samples. Each food sample should be somewhere about 1 centimeter, a little cube. It doesn't have to be exactly. It can be, it needs to just be a little piece of food, like kind of, and they should all be cut kind of the similar shape. Use things that you have around. Examples. It could be a piece of apple, or a piece of carrot, or a piece of cheese, or a piece of. I gave you. Sometimes we use, to be a little sneakier, use a piece of raw potato. Use whatever you have around. So, just scan around your refrigerator. Maybe a piece of cucumber. I don't know. Whatever. Avocado. It doesn't matter. They should just be 5 different kinds of food. These should be hidden from your subject. So you do this without your subject should not have any idea what to expect even. So you're going to prepare these 5 or 6 or however different samples. They're just sitting in a little bowl. You can have maybe a toothpick to pick them up or something. I don't know. So now you're ready to go. And now you have your subject. Probably leave their eyes closed because you don't want them to see the food and get any idea of what it might be just from what it looks like. And we'll talk later. That actually makes a difference. Just the color of something. If you're drinking juice or eating ice cream, if it's red or green, can totally make you mistake what you're eating. So no vision. And there's going to be 3 parts, 3 steps. The first part is just texture. So they hold their nose. So you put the thing in their mouth. They can kind of move it around on their tongue a bit, but no chewing and no smelling. They have to hold their nose, so no smelling. They don't bring the smell into their nose. And then can they record what they say? Maybe they say, I have no idea, or maybe it's a piece of fruit, but I don't know what kind or whatever. Just record. Record what they say. Part 2, include taste. So you continue to hold nose. But you now chew. So now you're chewing and you're smushing it around on your taste buds and your tongue. So you're getting the sense of taste in addition to the texture. Now you're going to record. Can they ID it now? You know, can I record what their experience is? And then finally 3, add in smell. Kind of let go of nose. And again there, can they ID it now and record what they find? So when you're doing this, before you start, make sure your subject really understands that there are 3 steps. For each piece of food, they're going to sit down, they're going to hold their nose, you're going to put a piece of food in their mouth, they just move it around their tongue, but they don't chew, and then they see what they can see. Can they identify it already or not? Then they continue to hold their nose, but now they can chew. See if they know what's in their mouth or not. And finally, add in the sense of smell. Let go of your nose. Now you got taste, smell, texture. Can they tell now? Find out how important is just pure texture or the taste or smell in actually identifying the food. Or is it the same across all foods, or is it different for different foods? And why do you suspect that? So you've got the whole weekend to do this. At some point, go, and I think you'll have fun with this. This one is a lot of fun. Again, I'm trying to figure out what should we do, what can we let go of, and you'll get through something else. But this one I think is really nice to do on your own, because it's really interesting to see how much what we normally think of as taste is really not about your taste buds. It's much more complicated. And in fact, your taste is just a little part of a much more kind of holistic experience of the food inside your body, there in your mouth. Any questions about this one? Okay, so, and I will say also that this will be the last of the labs before the lab exam, which is a week from today. We'll be covering the labs that we've been doing through the semester up to this. So nothing more than this. Next class, the next lab day is just going to be about kind of reviewing stuff for the lab exam. There's not going to be new lab stuff. We'll discuss the labs. I'll probably use some of the time to also do a little more lecture stuff, because I'm